All right, in this video we're going to do our first application of Bayes' theorem to a problem of inference. And to set up an easy case, we're going to imagine we're playing with a dice, so one of these, and then you roll it and it comes up with various numbers depending on the faces. All right, so these are dice, and if they're perfectly symmetrical, a perfect cube, then all the sides should be equally probable by symmetry, right? There's no reason to think that a 6 is more probable than a 1 or a 3 or a 2 because it's a perfect cube and all the sides are all equivalent to each other. So that would be a regular fair dice. Each number has an equal probability. Now we want to reason about a case where we go to Vegas and we're watching some dice game and we're suspicious that maybe the dice isn't completely fair. And to make a concrete example, suppose that the way the dice factory works is that there is they make dice out of very long stock of wood that's of a perfect square cross-sectional area, maybe 1 centimeter by 1 centimeter, and then the saw will cut it at regular intervals, hopefully exactly 1 centimeter, to make a bunch of perfect cubes. So the setup is like this. We have this something like this, and it extends out this way, and on this side, and now the saw will be cutting along here, right? And if these are aligned perfectly right, then all of these will be perfect cubes. But if the saw screws up and cuts it a little bit too thin, then we're going to end up with a tile-shaped dice that's going to have this kind of shape here. It's going to be thinner along one of the sides than the other ones, and in that case the number on the front and the back is going to be more likely to fall on those come up, because it'll look more and more like a coin. In the limit where this length was infinitesimally small, then the possibility that it'll land on edge will become very, very improbable, and only the front and the back will become the plausible numbers. So let's assume that they're always numbered so that the 6, and which on the opposite side, the 6 and the opposite side is the 1, are on these sides over here, and then there's a 1 on the other side. And we're going to assign Q to the frequency of 6s. So Q is the frequency of 6s, or now the other possibility is that it cuts it way too long, right? So then it comes out being longer on one side, and so it's shaped like a brick. And in this case, the 6 and the 1 are going to be less probable. Right here, they're going to be more probable than the 2, 3, 4, or 5, but in this case, they'll be less probable. You can just imagine then the limit where this brick becomes a rod, and then when you toss it, the chance that it'll stand on end will be very unlikely, and so you'll get way less 6s and 1s. And so in general, we're going to have this relationship that since there's two cases with frequencies Q, so we'll have 2 times Q plus, and if the side of the frequencies of 2, 3, 4, or 5 are all P, then 2Q plus 4P should be equal to 1. So that's the only possible cases. You either get 2, 3, 4, or 5, and there's 4 of those numbers, or you get a 6 or a 1, and there's 2 cases of that. And so the total frequencies have to add up to a 1. And so we're watching the dice being rolled in the Vegas casino, and we're suspicious that maybe these are not fair dice, and so we're going to try to estimate this parameter P. So our goal, so P gives us this parameter is related to the length, this length of the dice. If P is very small, then we have a tile shaped, and if P is very long, we get a brick. So it's not exactly the length, but it's related to it somehow. And we want to find out what this P, the parameter we're going to estimate, is precisely that bias parameter P. If the dice is perfectly cubical, then P should be equal to 1/6, which means that 2Q plus 4/6 is equal to 1, or 2Q is equal to 2/6, and that means that Q is also equal to 1/6. So it's a fair dice in that case. Okay, so how are we going to do this? So we're going to use Bayes' theorem to estimate this parameter P. So first of all, we need to, I'll remind you of the pattern. So Bayes' theorem. So we have the probability of the hypothesis. In this case is the value of p, so I'm just going to write the shorthand as p given, and we're going to have some data. So these are going to be the rolls of the dice, some data, and all this background information about the rod that we're sawing, the stock of wood, and the shapes, and the numbering ordering of the dice. So I'm going to call this I. So that is going to be proportional to the prior probability for p. So that's the probability of p, condition on the background information, multiplied by the probability of the data given p. And it's proportional. We don't need to worry about the normalization constant for now. And so now we need to come up with mathematical functions for the probability of p, the prior one, and also this function. Oh, and I need to put the, yes, condition on p and I over here. And we also need to come up with a probability for the data conditioned on the value of p. So we're going to want to get this one, but I claim that it's going to be easier to assign these two. All right, so first, what's the prior probability of p? So we know that p, right, is the frequency at which the 2, 3, 4, or 5 comes up. And so the smallest value that can have is 0. Maybe they never come up in the limit of a tile. And at the other extreme is that the rod is really long, and then the 6 and the 1 never come up, in which case the p will have to be 1/4, right? There will be equal probability for 2, 3, 4, or 5. Remember, just to remind you of the terminology, this is called the posterior. And this one, which is the probability of the data, is the likelihood. All right, so we're going to Vegas, and we're going to watch this roll of this dice go by that we're suspicious about, and we're going to collect some data. So this is going to be our data set here. And suppose right now I'll just do it for 4 rolls. So the first roll, we get a 4, then I roll again, I get another 4, and then another 4, oops, and then a 6. All right, so this is my data set. And so what we have to do is assign functions to these two probabilities, and then stick in the data where we have the data, and then this will give us the posterior probability for the value of p. So that's the way we're going to do it. So first we're going to reason about the prior probability for p. So remember, p was the frequency of 2, 3, 4, or 5. So in the limit where we have a tile, p would be 0. So p is going to be in some interval between 0, and the biggest value you can have is 1/4, right? Because p is the frequencies of 2, 3, 4, or 5. There's 4 cases, and we're assuming there's a perfect symmetry between 2, 3, 4, 5, so they have all the same frequencies. And so the biggest value p can have is 0.25. So the parameter p is somewhere in this interval, and so the probability density for p, so the prior, which is the probability density of p, is going to be 0, I guess. I'm going to start with 0 if it's outside this range. If it's p is less than 0, or p is greater than 0.25. On the other hand, if p is in this interval, then we're going to give it equal probability to every point on the interval. And so the probability we're going to give it is going to be 4. And this, remember, it's bigger than 1 because it's a probability density for p in the interval of 0 to 0.25. And the reason we give it 4 is because the total probability has to integrate to 1, right? So the graph of the prior is going to look something like this. So it's 0 out here, this is 0, this is 1/4, and this is p. And out here this has to be 4, so that the area here is equal to 1, right? 4 times 1/4 is equal to 1, and that's the total probability. So remember, this here in this case is a probability density. It's the amount of probability per unit interval dp, and it has to integrate to 1. All right, so this takes care of this one, the prior. And now we have to think about the probability of the data. And just to keep everything neat, I'm going to express this in the following way. So they're going to be what we got on the first roll, I'll call this R1. What we got on the second roll, R2. So R1 is equal to 4, R2 is equal to 4, R3 is equal to 4, and so is, no, and R6 is equal to 6. All right, so we want to write the likelihood, which you'll remember is the probability of the data conditioned on the model or the hypothesis, or in this case the parameter p, and that's going to be equal to the probability of. And now we're going to break this up using the product rule. So this becomes the probability of R1 times the probability in R4 conditioned on the value of R1, P, and I. And we're going to use the product rule in the second one again, so that's the probability . All right, so now we've broken up the joint probability for R1 through R4 into a product of 4 conditional probabilities. The first one, R1, is not conditioned on anything except P and the background information, but R2 is conditioned on what we got on the first roll, R3 is conditioned on what we got the first and second, and R4 what we got on the first, second, and third. And so this is a very general case. Now, if we're assuming that what we got on one roll doesn't influence in any way what we're going to get on the second roll, and then in that case, we can assume that what we get on the second roll is independent of what we got on the first roll. So the information we got on the first roll doesn't tell us anything about what we're likely to get on the second roll. Now you might say, well, wait a minute. The whole point is we're rolling the dice to try to find out, to make predictions. So how can it be that what we have at one roll is independent of what we're going to get at the next roll? So we're going to assume independence conditioned on knowing P. So if we know the value of P, then in that case, knowing what we got on the first roll adds no extra information. And so then we can just say that the probability of R2 given R1 and P is the same as probability of R2 just given P. And so R1 didn't add anything, conditioned on us also knowing P. And similar here, we're going to say that R3 is independent of what we got on roll 2 and roll 1. Again, conditioned on knowing P. If we didn't know P, then that wouldn't be independent, right? Because, for example, we may not know that the dice is totally loaded and P is equal to 0, but if we've rolled the dice 100 times, then we've noticed that all we've ever gotten was 1s and 6. And then so the prior information is really relevant to knowing what we're going to get on the 100th roll. And so the 100th roll is not independent of what we got on the 99th, 98th, and so on. But if we know P, then it is independent, or that's going to be our model. And so then what we get is the probability of R1 given P and I times the probability of R2 given P and I. So the fact that we can multiply all these probabilities is because there are all the events, all the data are assumed to be independent. So this is an example of independence, and we can just multiply the probabilities. If not, we have to use the conditional. If they're not independent, we have to use the conditional probabilities. All right, so in this particular case, for our particular example, this data set, this would be equal to, so the probability of R1 is a 4, and so the probability of a 4 is P. The probability of R2 is again a 4, which is also P. R3 was also 4, which is P. And the probability of, this is R4. The fourth roll, which was a 6, and that's a Q. So in that case, we would say that the likelihood is equal to P times P times P times Q. And Q, we can write it in terms of P. So this is 3 times, is p cubed times q, which is, what was q? Q is, we know that 2q plus 4p is equal to 1, and so 2q is equal to 1 minus 4p, or q is equal to 1 minus 4p divided by 2, which is 0.5 minus 2p. All right, so this is for this particular data set that we have. This would be the likelihood. So now, so far, we have likelihood. We have the likelihood over here. We have the prior probability, and if we multiply them together, we'll get the posterior probability. So the probability after these first roll, the probability of p, condition on this data set, is going to be proportional to the prior, which is, in this case, is just 4 times this quantity, p cubed times 0.5 minus 2p. And it's only proportional, so there should be some normalization constant. If we want to make it equal, we would say it's 1 over z times 4p cubed 0.5 minus 2p. And to find out what z is, we would want the area under this function to be equal to 1. So that means that the integral from 0 to 1/4 of 4p cubed times 1/2 minus 2p dp divided by z is equal to 1. And that's going to allow us to decide what z is. 8p to the 4th power dp, and we can actually calculate it. It's going to be equal to, the integral of p cubed is 1/4 p to the 4th, so that's going to be 1/2 p to the 4th minus, and this will be 8/5 p to the 5th value between 0 and 1/4, and that's equal to, yeah, and then we can evaluate, we can plug in the numbers and find out what we get. All right, so we're going to code up this example. We're going to do what's called a Monte Carlo simulation. We're going to use MATLAB's random number generator to simulate cases with such a biased dice. We're going to use Bayes' theorem to try to update our probability for the value of p. So we start off with this flat prior, where p can be anywhere on the interval from 0 to 1/4 with equal probability. And as we collect more and more data, we'll see the probability shift and change based on the new information we have. All right, so I've already created a program which I've called dice. So p is this parameter, this bias parameter. I made a perfectly fair dice. The value of p is 1/6, so that means q is also 1/6, so all the numbers are equally probable. And we're going to simulate 1,000,000 rolls of this dice. So that's the nice thing about the computer. You don't get tired of rolling the dice. And I made this little program called roll, and it will roll the dice n times. Based on this parameter p, will give us a random data set of 1,000,000 rolls in this case, or n rolls, assuming the value of the parameter is p is 1/6 in this case. And then we're going to make a histogram of the data set of R. So R will be 1,000,000 numbers which are random, and they're going to be discrete numbers between 1 and 6. Okay, so this is the histogram of the counts of how many times we got a 1 through a 6, and they're all fairly equal because I have 1,000,000 rolls and I put p to be a fair dice. I could make this number smaller. So these are the frequencies, and now you can see some variability because I only have a small data set. So the data set is R, and these are the particular numbers I got in this case. And this was for a dice that was fair, but of course if I was to run it again, and I get another data set, and run it again. All right, but if in the limit where I pick more and more rolls, here I have 100,000, 1,000,000 again, then the variance here are very small compared to the total number of rolls, and it starts to even out. So that's the kind of the frequentist view of probabilities, where they define the probabilities as being this long-term limit where things will go in the long run. I could also change the value of p, so it's interesting to pick a different value of p. So if I pick p to be 0, for example, and now the only options are 1 and 6, so these have equal probability, roughly about a half, and the other ones 2, 3, 4, and 5 never come up. All right, so that's, oh, I should show you what this roll subroutine does. So that's in this file. Here it is. So this is this Monte Carlo function here, roll, and it'll simulate random draws of this funny Vegas dice. So the way it works is I first create R, which is a vector of zeros for the n rolls. So I pass in p and n, and then I compute q. Remember, q is a half minus 2p, right? That's the q is the probability of getting a 1 or a 6. And then I made a cumulative probability density function. And so what I do is I come in, p is that parameter, I compute q, and then I make the probability between 0 and 1. From the end, I have the length q, and in the middle, I divide it into 4 equal parts length. And then I'm going to draw a bunch of random numbers along this direction. And now I check if x is greater than the cumulative sums. Now this number here fell between q and q plus p, so this, we would want to assign this a 2, and so what we're going to do, so this would correspond to a 2, this one falls between 0 and q, this would correspond to a 1, and this one falls between q plus p and q plus 2p, that would be a 3, this one falls between q plus 3p and q plus 4p, that's going to be a 5, and this one is going to be a 4. All right, so the way the code works to make this efficient is I compare the number x1 to the cumulative sum. So I check if x is greater than these numbers. So if x is not greater than 1/6, then I assign a 0 to the first number. So it'll be 0. And it's not going to be, if it's not greater than 1/6, it's not going to be greater than any of them. So that would be all zeros in that case. But in this case, it was bigger than 1/6. First number would get a 1, but it's not bigger than q plus p. So then it gets a 0 for all the other checks. For the second number, which falls here between this interval, it's going to be bigger than the first q. So I get a 1 here. It's going to be bigger than q plus p. It's going to get a 1 here, but it's not bigger than this one. So that condition here, x greater than c, is going to get a 0 for all the other ones. And for this one, it is not bigger than q, so I get a 0, and of course it's going to be 0 for all the other ones. For this one, it's bigger than q, so I get a 1. Bigger than q plus p, I get another 1. q plus 2p, 1 again. q plus 3p, 1 again. But q plus 4p, it's not going to be bigger than that. So then I get 0 and 0. And the last one will be 1, 1, 1, 0, 0, 0. And then I sum these columns. So if I sum these, I get 1, 2, 0, 4, and 3. And then I just add 1 to that, plus 1, and that gives me the 2, the 3, the 1, the 5, and the 4. And so that's what this line does over here. Probability distribution in terms of q and p into a quick way of extracting what number of the roll that would be. So now I'm going to start a simulation, and I'll explain how the simulation works after. Okay, so now we're ready to do the simulation. So down here, I have the probability density of p. So this, I haven't made any rolls, so after 0 rolls, so this is what I would call the prior. And so it's got equal probability for every possible value of p between 0 and 1/4. And it's a probability density, so the height of the probability density function is 4, and that's so that the area, the total integrated area, is equal to 1. So it's a properly normalized prior probability for p. And then I'm going to hit return, and now we got the first roll, which we got a 5. And after a 5, I updated the probability of p conditioned on the data, and now I have this new probability density function. So now it's like a linear function with 0 all the way up to a maximum at 1/4. So what happened here? So given that I got a 5, that means the value of Q cannot be a half, right? So the value of P cannot be 0, because if P was 0, then a 5 would have been completely impossible. So it just took one rule for Bayes' theorem, which is implemented in my code for my robot, to deduce that the probability density has to be 0 at the value of P equals 0. And in this case, it just increases linearly after one roll. And in this graph, what I plotted is something called the mean of this distribution, and the whiskers on either side, these are called one standard deviation. So I'll explain what these are. So let me make note of this: the mean and the standard deviation. So I will define these things in a little bit. But you can sort of think of this as being the most probable estimate for the value of P, and this is kind of like a range, an error bar on that value. All right, so hit return again. So this time I got a 1. Given that I have 1, that means that the value of P cannot be 1/4, right? Because if P was 1/4, then a 1 in 6 would be completely improbable. And since I got a 1, then it cannot be that P is equal to 1/4. So now the probability distribution is just bent over like this parabola, and it's now contained between 0 and 0.25. And now this here is the new updated mean and standard deviation of this probability distribution. And remind me, I have to explain what mean and the standard deviation is. Now I roll again. I got another 1, so that makes this end of the probability distribution even less likely. And we're going to keep rolling, adding more data: 5, a 1, another 1, a 6, a 1, 2, and then we can keep going, and it's updating. Now, when I did the simulation, I didn't show you the true value of P that I did to simulate the data set was 0.1. So you didn't know that, and my program, the program that generated the data, knows that the value of P is 1/2, but the algorithm that's generating these posterior distribution doesn't know the value of 0.1 for the true value. It's trying to estimate it, and it's updating the probability as the size of the data set increases. So this is the number of rolls. So we're all the way up to 15 rolls, and this is the posterior probability. Oh, sorry, we're up to 17 rolls. 17 over here, and this is the posterior probability of the value of P conditioned on the data after 17 rolls. And let's keep rolling. And you should see the probability density getting narrower and more clustered around the true value of 0.1. And one thing you notice is that after the data gets very big, we're up to 338 rolls, the changes get smaller and smaller. So to get big changes, if you have a lot of data, you have to like double the size of the data set. So the rate of increase is slower and slower. The rate at which your error bars decrease, they increase sort of like the square root of the number of rolls. So it gets sort of slower and slower as we go along. So 0.1 is a little bit less than 1/6. Right, it's 1/10, and so that means that the 1 and the 6 are a little bit more probable than the 2, 3, 4, or 5. So right now I'm up to 644 rolls, and 0.1 is still a plausible value, but so far, based on this random data set, we would think that a value of 0.12 is maybe more probable. But let's see if it recovers as we gather more and more data. All right, so this is where again. So the last value that we estimated, p hat was 0.106 plus or minus 0.003. That was the standard deviation. And so 0.1 is still in the interval. Of course, there's a random data set with 1,000 rolls, so we can't get the precise value. We'd only get it in the limit where we take an infinite number of rows, but I can run it again. Right, so that's the second experiment. So you see that the PDF, this time I did 2,000 rolls, and at the end the PDF is very sharply peaked around the true value of 0.1. So we would have a pretty good estimate, and you can see that the error bars are getting narrower and narrower, and that's because this distribution is getting more and more sharply peaked as the number of data sets gets higher and higher. And so this is the posterior PDF of the value of P conditioned on the data, computed using the formula for Bayes' rule, and I'll go through in the next video how this was coded up. But for now, I first want to explain to you what the mean and the standard deviation is. So if I have a probability density function f, then the normalization condition is the following, to 1. So that says that the total area under this curve is 1, so that there is a unit amount of probability in total. So this is the normalization condition. And then we're going to define what's called the expected value of some quantity, in this case x, in this way. So that's the integral from minus infinity to plus infinity of x times f of x dx. And this quantity, called the expected value of x, is what we call the mean of the distribution x. Is the mean of the distribution f of x. So this is the mean. So it's like the weighted average of the values of x, where the weights are given by the probabilities, f of x dx. So remember, f of x dx is the amount of probability between x and x plus dx. So these are the weights, and we're going to sum all the possible values of x, and in that sum we're going to weight them by the probability. And then we can define the variance, x minus its mean, all squared. So we take x, we subtract its mean, we square it, and then we take the expected value. So that is equal to this following quantity, minus infinity to infinity of x minus the mean of x. Remember, the mean of x is just going to be some number. We've already computed it. We square and we weigh it by f of x dx. And this we call it the variance. So it's like the expected value of the squared deviations from the mean. So if x is always very closely clustered to the mean, then x minus its mean is always going to be a very small number, and then we square it, we always get a positive number, so the variance will be small. And then the standard deviation is going to be the square root of the variance of x. So those were the quantities I was computing with the error bars. So I was plotting the mean. My graph was like this, for example, and this was the mean, and this here, from here to here, was one standard deviation. So this was x plus the square root of the variance of x, and down here I had x minus the square root of the variance of x. And now if this probability density function f of x is a normal distribution, then probability in this range between x plus the variance, the square root of the variance, minus x minus the variance is about 60%, 67%, and 67% of the probability. Mu minus sigma and mu plus sigma. And what's mu? Mu is another name we use for the mean, and sigma is another name we use for the standard deviation. Alright, so that completes this video. The next one will explain how the Bayesian dice p estimating parameter works.